Hey there and welcome. We're about to do something pretty cool. We're going to take what might feel like a really dry physics lesson and turn it into the key that unlocks a much deeper, more confident understanding of audiology. Okay, let's get into it.
So think back for a second. Remember all those physics formulas from your first year? The ones you thought, okay, I just have to get through this.
Well, what if I told you they weren't just hurdles? What if they were actually the secret code? The key to really understanding what's going on inside the ear and making those sharp, accurate clinical judgments.
Well, that's exactly what we're going to do right now. In just the next few minutes, we're taking 4 basic physics concepts and turning them into a brand new, powerful diagnostic toolkit you can use every single day. All right, first up, pressure. And look, forget the complicated formulas for just a second. Let's reframe this. Think of pressure as your way of seeing the invisible. Seriously, it gives you this crystal clear picture of what's happening inside the middle ear, all without ever having to look inside.
So here's the key thing to get. Pressure isn't just about raw force. Nope, it's all about how concentrated that force is. The formula is super simple, right? Pressure is just force divided by area. So if you take a whole lot of force and you focus it on one tiny little area, you get a ton of pressure.
And this is the perfect way to think about it. Imagine you're pushing on a wall with the palm of your hand. You're using force, but nothing really happens, right? But what if you use that exact same force to push a thumbtack into the wall? It goes right in. Same force, just a much, much smaller area. And boom, immense pressure. That's the secret sauce we use in the clinic every day.
Okay, so how do we actually use that thumbtack idea? Well, this is where it gets really cool. In tympanometry, we're basically using a gentle puff of air to push on the eardrum. If the ear is healthy and everything's moving like it should, the eardrum moves easily and we see that nice clean peak on the graph. But what if there's fluid stuck behind it? Well, that fluid pushes back. The eardrum is stuck. It can't move. And what do we see? A flat line. It's that simple. Just by understanding pressure, you can instantly see the problem.
Okay, so we've got this idea of force. Let's build on that. Our next concept is actually a duo, work and energy. Now, don't think of them as two separate things. Think of them as the dynamic duo, the engine that powers the entire mechanical part of hearing. You know, in physics, the word work has a super specific meaning. It only counts as work if a force actually makes something move. We call that displacement. So you could push against a solid brick wall with all your strength for an hour straight, you'd be totally exhausted, right? But because that wall didn't budge, in the world of physics, you did zero work. None.
And this is exactly what those tiny little bones in your middle ear, the ossicles, are doing all day long. They apply a force to the oval window, which causes it to move, to be displaced. They are doing real, actual, measurable mechanical work. And that's how they pass the sound vibration from the eardrum into the cochlea.
Now, to do any kind of work, you need energy. And we can kind of split it into 2 main types. First, you've got potential energy. That's stored energy, just waiting to be used, like a spring you've pushed down. Then you've got kinetic energy. That's the energy of motion. It's that same spring after you let it go and it pops up.
The swinging pendulum is just the perfect way to see this in action. Picture it. At the very top of its swing, it hangs there for a split second, right? At that moment, all its energy is potential. It's stored up. Then, as it swings down, that potential energy starts converting into the energy of motion, kinetic energy. And right at the very bottom, when it's moving the fastest, that's maximum kinetic energy. It's just this beautiful, constant dance back and forth between the two.
So why on earth does this matter to you in the clinic? Well, because our entire field is built on this idea of energy conversion. Think about it. The cochlea's whole job is to take that mechanical energy from the ossicles and convert it into the electrical signals the brain can actually understand. And what do our devices do? Hearing aids, cochlear implants, they do the exact reverse. They take electrical energy from a battery and turn it back into sound energy for the patient.
Okay, so we've got the energy. But how fast we use that energy is just as crucial. And that brings us to our third concept, power. Power isn't just about being strong, it's all about the speed of delivery. So power is defined as the rate at which energy is used. And that word, rate, is everything. It's not just how much energy you're using, but how much energy you're using per second. That's why the formula is work or energy divided by time. The unit is the watt, which is really just a fancy way of saying a joule per second. So let's say you're looking at a hearing aid spec sheet, and you see a number like this, 10 milliwatts. Okay, 10 milliwatts.
But what does that actually mean for your patient? How does that number on a piece of paper translate into what they actually hear?
It's simple, but it's so important. It means that device is delivering 10 millijoules of sound energy to their eardrum every single second it's on. Understanding power is what lets you set the right gain. It's how you make sure the device is delivering energy at the perfect rate for your patient's hearing loss. It is all about the speed of delivery.
Okay, let's pull it all together now. Pressure, work, energy, and power. These aren't just 4 random concepts from a textbook. They are a single, unified toolkit. And when you see how they all connect, well, that's when this stuff becomes your clinical superpower.
So here it is, your new physics toolkit, all in one place. Pressure? That lets you see fluid with tympanometry. Work? That's how we describe the ossicles moving. Energy? That's the currency that the cochlea and hearing aids are constantly converting. And power? That's how you measure the output of those devices. See? They all build on each other, one after the other.
All right, you ready for a quick pop quiz? Let's test this out. Imagine a tiny compressed spring inside a hearing aid, just waiting to be released. What type of energy is it storing? Is it A, kinetic, B, chemical, or C, potential? Go on, take a second.
And the answer is C, potential energy. That's right. Remember, any stored energy that's just waiting to do work is potential energy, just like that pendulum at the top of its swing.
Okay, let's try one more. You've got a hearing aid, its power output is constant. Now, if you make a sound last for 2 seconds instead of just 1, what happens to the total energy that gets delivered to the ear?
It doubles. You got it. It goes right back to that simple formula. Energy equals power times time. So if the power stays the same, but you double the time, you're going to deliver twice the energy. It's that direct.
And really, that's it. These concepts, they're not just for exams. They are the fundamental code behind everything we do in the clinic. So now that you can see that code a little more clearly, what other clinical mysteries are you going to solve with your new physics superpower?